This is Transmission Line Theory and Time Domain Reflectometers by Zachary Wade. In order to talk about TDRs, time domain reflectometers, we have to talk about transmission line theory first. In standard circuit analysis, transmission line effects are usually ignored due to the lack of their effect in low frequency analysis. But when you have transmission distances that are over 0.1 of the wavelength of the frequency of the waveform you're sending, the effects must be accounted for. This is because wave properties such as reflection are now relevant. The main wave property we're concerned with when looking at transmission line theory is reflections. It's very similar to a rope on a wall that you might have seen in an intro physics class, where they send a pulse along a rope and then when it hits the wall it bounces back. For circuits, this effect occurs between elements with different impedances, and it will act like ropes with different densities that are connected together, like in the bottom right picture, where when a pulse is sent along and it hits a more dense section of rope, a secondary smaller pulse continues on, but a reflection gets sent back. And whether or not it's positive or a negative reflection depends upon the difference in impedances. This effect is where a TDR comes into play. Now finally on to what a TDR is. A TDR will commonly resemble the image in the top right. Usually has a screen, buttons, and to be honest, might just resemble a fancier multimeter or some kind of handheld oscilloscope. But what it does is very different. Its primary thing that it has is that it can read waveforms on the nanosecond or smaller scale. And this is to accommodate the fact that circuits might reach steady state extremely quickly, and you want to see how it got to steady state. In its most simplistic form, it's basically a voltage source connected to a source resistance with a voltmeter in parallel that you then connect to some transmission lines. But the reason you'd use a TDR is that if you're using a cable and it has a non-continuous impedance due to a kink or a break, and you want to know where in that cable that break is, or even if one exists, you can use the TDR to measure that cable and see if a reflection comes back. If you want to check if your circuit's impedance matched correctly, you can throw it in and see if a reflection comes back at all, which if impedance matched, it shouldn't. You can also determine the velocity factor of a cable, which is how fast it propagates a waveform compared to the speed of light. If you know the distance of the cable, it will measure the time it takes for the reflection to come back. You can also tell how far in a cable an issue is. If you know its velocity factor, it times how long it takes for its pulses to go out, which then can tell you where in a cable an issue might be. For our first transmission line scenario, we're going to look at an open circuit. It's important to note that for all of these scenarios we look at, our TDR's resistor is impedance matched with the transmission line. What this means is any voltages coming back at the TDR will have a reflection coefficient of 0. They won't cause any reflections again back into the circuit. For our open circuit with our TDR connected to our transmission line and then the open on the load end, we end up getting a reflection coefficient of 1. So on our voltage readout on our TDR, we start out reading just the voltage from the source, but at time 2 capital T is the amount of time it takes to actually traverse a transmission line. So when it's traversed and then come back, we end up reading a value of 2 times the voltage source. This is because the reflection coefficient is 1, which means that a mirror waveform gets reflected and goes all the way back to the TDR, which will constructively interfere with the initial waveform. For this transmission line scenario, we're going to look at a short circuit. We have our TDR connected to our transmission lines, leading into a short circuit on the load side. In this case, the reflection coefficient off the load side ends up being a -1 because we get negative Z over Z. On our voltage readout on our TDR, we see that initially we start out with the voltage source again, and at time 2t, when the reflection finally propagates back, that -1 waveform is going to deconstructively interfere, effectively deleting the waveform, resulting in a voltage readout of 0. For our first proper transmission line scenario, we're going to be looking at a resistive load. In this case, we have two scenarios we really care about here, where the resistance is either less than or greater than the impedance of the transmission line. For both cases, the TDR is going to start out reading the voltage source value, but at time 2t, when the reflection propagates back, whether the voltage goes up or down is going to be based on whether the resistance is less than or greater than the impedance of the transmission line. If it's less than, you're going to get a negative reflection coefficient, lowering your voltage. And if you have a greater resistance, you're going to increase your voltage. The maxes for either of these are going to be 0 volts for the less than, or 2 times the voltage source for the greater than, based off of our short and open scenarios. For our second transmission line load scenario, we have a capacitive load. You can see on the output of the TDR, once again, we start off reading our voltage source, and at time 2t, we're going to go down to 0 volts and then exponentially increase to the asymptote of 2 times the voltage source. This is because this is the transient response of the capacitor. It's going to start out as a short circuit, which drops us to 0 volts, as we saw earlier, and then over time it will hit an open circuit, which brings us to 2 times the voltage source. For our third transmission line load scenario, we're going to have an inductive load. Once again, on the TDR output, we're going to see the voltage source up until time 2t, when the reflections propagate back. We're going to see it spike up to 2 times the voltage source roughly, and then exponentially decrease to the asymptote of 0 volts. This is because, as a polar opposite to the capacitor, the inductor starts as an open circuit and then continues on until it reaches a short circuit. For our case 4, we're going to be looking at a slightly more complicated example. For this one, we have a TDR connected to a transmission line that feeds into a junction created of a resistor, capacitor, and another set of transmission lines that then eventually has a load that's impedance matched to the transmission line. Because of this setup, we have a 0 reflection coefficient off of the TDR, as explained in the previous examples, but we also have a 0 reflection coefficient off of the load due to its impedance matched nature, which means the only place we're going to see any reflections is off of the junction on its way back towards the TDR. So to start off with, we're going to have the voltage source value reading on the TDR up until time 2, when this reflection can come back. The equivalent circuit that the waveform that's propagating forward will see is this one when it hits the junction, with the resistor leading into the capacitor and the transmission line in parallel. The initial condition for this is the capacitor acting like a short circuit, which means that all of the current's going to flow through it to the ground, back to the TDR to the ground. So in this case, the only thing that the waveform sees is the initial resistance, which is impedance matched, meaning that we're going to have a reflection coefficient of 0 to start out with as our initial condition. At final, though, we have the capacitor acting as an open circuit. And when it's an open circuit, what our circuit sees is our resistance going into the transmission line in series, which is going to end up being 2Z0 minus Z0 all over 3Z0, which is also equal to 1/3. Because of this, a positive 1/3. Because of this, we're going to start out at Vs, and then we're going to go up like that to an asymptote at 4/3 Vs, and continue on that for the rest of time. For our last case, case 5, we have the same setup as case 4, except our junction is a little different. Where instead of, for our initial resistor, we now have an inductor, and where our capacitor was, we now have a resistor. Once again, the reflection coefficient off of the source, TDR, is 0, and the reflection coefficient off of the load is also 0 due to its impedance matched nature. The effective circuit that our initial waveform propagating forward sees is this one here, with the inductor leading into both to the resistor and the transmission line in parallel. In this case, our initial reflection coefficient is going to be 1 because the inductor is going to act as an open circuit initially, causing the reflection back to be 1. For our final reflection coefficient of where we're going to end up, our inductor is going to act like a short circuit. And in that case, we're going to only see the two resistances in parallel. In this case, R in parallel with Z0, because R is equal to Z0, is going to be equal to 1/2 Z0. So for this case, our reflection coefficient is going to be 1/2 minus 1 all over 3/2, which is equal to a negative 1/3. Because of this, because of our initial condition, we're going to go up to 2Vs momentarily, and then we're going to exponentially decrease and approach an asymptote that our circuit will reach steady state at 2/3 Vs.